Hello everyone. So I'm going to present our project entitled Probabilistic Constraints Stochastic Optimization for Supply Chains. It is done in collaboration with Dr. Nadim Rashid and Professor Al-Tamponi. And by the end of this work, we successfully introduced our stochastic optimization problem for supply chain inventory control, and we proved the efficiency of our approach for sensitivity analysis. In fact, in this work, we started by studying chemical reaction modeling. We introduced the stochastic reaction network, which is a system involving multiple chemical species and reactions, where each one of them is modeled as follows. And to simulate exact path of a given stochastic reaction network, we can use exact algorithms such as SSA. However, they are computationally feasible only for relatively low propensities. So therefore, we use the Taulip approximate scheme. And since we consider the consuming delayed reactions, we introduce the delete method, which takes into account delay, and we include the necessary informations to ensure the Markovianity. After studying chemical reaction modeling, we study its analog with supply chains. And as we can see in this example, in supply chains, raw materials are annihilated in the first stage. They go through different processes to become intermediate parts, and in the last stage, final products. And these processes, in fact, are the analogs of the chemical reactions, and these type of parts are equated with the molecule species. Therefore, we study the analogs of the exact algorithms to simulate supply chains, such as the DES. We also study the time bucket method, which accelerates the simulation, and we introduce the LLIP scheme, which takes into account delay and the characteristics of supply chains. We simulate the stochastic system using the LLIP method, and we visualize 100 paths over the period of 400 days for different time buckets. These simulations highlight the importance of inventory management. Therefore, we introduce two strategies. In the first one, we update the inventory with the replenishment order quantity whenever it falls below the safety stock. And in the second one, we consider raw material acquisition processes as pure burst stochastic reaction networks where the acquisition rates lambda I have the following exponential expression to capture the same policy of the first strategy. We will focus on this method and work on optimizing the control variable theta, which is the vector composed of these coefficients. Now we focus on the optimization of supply chains. We formulate an inventory control for a push system with multiple processes not necessarily arranged in tandem, aiming to find the optimal parameters of the acquisition rates while minimizing the cost of storing the parts over the time horizon and the unsatisfied demand under the constraint of order satisfaction. And since the state vector is stochastic and the constraints are probabilistics, we opt for change constraint optimization and we use large deviation to approximate them, and we end up with this expression for rare events. And in the numerical optimization, we will need to compute the gradient of the objectives and the constraints. Therefore, we study the sensitivity analysis or the gradient composition of function of this form for four different methods. So the first one is variance difference, to which we add the coupling to reduce the variance reduction. And then we extend coupling to use importance sampling. And finally, we introduce our likelihood-based approach, where we use importance sampling twice for a fixed reference value theta bar. We plot the derivatives of this expectation with respect to the same theta k for four methods: variance difference without coupling, with importance sampling, and for our likelihood-based approach, and construct a 95% confidence interval to compare their efficiency for two experiments, one with constant and the other with time-dependent rates. We conclude the efficiency of our approach in variance reduction as well as computational savings. Thank you.